Hi y'all, so we are going to discuss the atomic spectrum, which is the behavior of light in this video today. So in the past you have probably been exposed to this diagram of the electromagnetic spectrum, which lists all of the wavelengths and types of light from usually longest to shortest wavelength or lowest to highest frequency. And so we can see that in a given beam of light, we have a bunch of different types of electromagnetic radiation all packaged into one beam. So it starts at the low end with radio waves, which are from about 10 to the 4th meters to 10 to the minus 2 meters. And that includes like all of your AM, FM, shortwave radio, as well as the frequency that your TV usually operates on. Then from about 10 to the minus 2 meters to 10 to the minus 4 is your microwaves. So like the microwave you probably have in your house to heat your food with. And from 10 to the minus 4 to right about 10 to the minus 7 is the infrared radiation. So that's what they can use for like night vision heat goggles, or what they're using right now in the scanners that they use to scan you when you go into school every day to see if you have a fever. And then this tiny portion right here is the visible light spectrum. This is the only part of this whole spectrum we can actually see. And it's got a very narrow range of wavelengths from 7.5 times 10 to the minus 7 meters to 3.8 times 10 to the minus 7 meters. Or sometimes it's more commonly referred to as 750 to 380 nanometers. Again, it's all the colors of the rainbow in order from longest to shortest wavelength. And that would be the Roy G. Biv mnemonic you may have been taught in the past to remember the colors of the rainbow. You know, red, orange, yellow, green, blue, indigo, and violet. So once we get above 380 nanometers, between that and about 10 to the minus 10 meters is the ultraviolet spectrum. And that would be like your UVA and your UVB rays that you use sunblock to protect yourself from. It's also what they are experimenting with in order to make really high-tech like DVDs. Then from 10 to the minus 10 to 10 to the 14th meters is X-rays, like you go get an X-ray at the doctor if they think you broke something. And then also from about 10 to the minus 10 to 10 to the minus 14 is gamma rays. So these two parts kind of overlap each other, and that's because usually when they take an X-ray, they're using a radioactive particle to image the bone, and when any kind of radioactive decay, usually there's also some emission of gamma rays. So most of the spectrum you're exposed to every day, and you never know it, and it never hurts you because it doesn't have enough energy to really do anything to you. It's not until you get up above the visible spectrum that we're talking about enough energy to actually do damage to cells. And so like you can get a sunburn or long-term exposure to this, to X-rays. You can end up with getting cancer, but you'd have to like take an X-ray every second for like a month for it to do anything. But even short-term exposure to gamma rays can cause some pretty serious problems. And all of these frequencies and wavelengths of electromagnetic spectrum travel at the speed of light, which is a constant 3 times 10 to the 8th meters per second. So we view light as having both characteristics of particles and characteristics of waves. It acts like a wave in that it has a wavelength and a frequency, and it travels at a certain speed. So if y'all don't remember from past classes where you've studied waves, wavelength is the distance between two corresponding points on adjacent waves. It's usually measured as from crest to crest. So let's see. So like if I draw this wave, then this is the wavelength. All right. Then they also have a frequency, which is how many wavelengths pass a certain point at a given time, which is usually the number of waves per second. And that is referred to as the hertz. So here, this would be a low frequency wave, and then this would be a high frequency wave. If these are both traveling at the same speed, then fewer waves are going to pass a given point per second with this wave than this one. And so these are related mathematically using the expression speed of light equals wavelength times frequency. So that means that the frequency and the wavelength are inversely proportional to each other. If one increases, the other decreases. And so again, if we look at these two example waves, this one has a long wavelength and a low frequency. This one has a short wavelength and a high frequency. So they are inverse to each other. And of course, that's going to stay on there. So now we're going to erase this. So if we want to do an example problem in determining either the wavelength or the frequency of a wave, if we know the other variable, we would look something like this. So let's say I want to determine the frequency of light whose wavelength is 4.25 times 10 to the negative 7 centimeters. All right, so first off, wavelength in these kind of equations need to be expressed in meters. So I would need to convert this to meters. So there are 100 centimeters in a meter. So I would divide my centimeters by 100 to make it into meters. So this would be 4.257 times 10 to the negative 9 meters. Then I can use the triangle of doom expression to rearrange my speed of light formula to solve for the frequency. So if I want frequency, I can see that speed of light divided by the wavelength. So I get this formula, and then I can plug in my values for speed of light, which is 3 times 10 to the 8th, and the given wavelength, and divide them and solve. And then when I'm rounding these to sig figs, I do not look at my constants for my sig figs. Constants can technically go out to forever. It just depends on where somebody randomly decided to cut the number off. So I'm going to get my sig figs from my given measurement. So this number here has 4 sig figs. Remember that all the numbers in front of the coefficient that are in the coefficient are significant. So that's 1, 2, 3, 4. So then I would round my answer to 4 sig figs, and I would get this 7.047 times 10 to the 16th hertz. So that was how light can behave like a wave. You know, it acts like a wave, it carries energy, it has a frequency and a wavelength. But it can also act like a particle. And the fact that light can be considered a particle helped explain a certain phenomenon called the photoelectric effect. And that was when light would strike metal and cause this effect, but it didn't work for all frequencies of light. And that wasn't explained well using wave theory of light. It did not explain why there was a minimum frequency needed to produce this effect. So then Max Planck got the idea that, well, light can also act like a particle. And specifically, it can carry a discrete amount of energy called a quanta, which is how much energy can be lost, or the minimum amount of energy that can be lost or gained by an atom. And so if it's going to carry a certain amount, then it must be behaving like a particle, is what he said. And he even quantified that by saying that the energy of the photon that is carrying this energy would be equal to its frequency times a constant that he derived, which is now called Planck's constant, which is this h, 6.63 times 10 to the negative 34 joules seconds. And so that means that the energy and the frequency of the light are going to be directly proportional to each other. If the frequency of the wave increases, then the energy it's carrying will also increase. And so we had this wave nature theory and we had this particle nature theory. And then in 1905, Einstein combined them to say, well, it has a dual wave particle nature, and also defined a photon as the particle of electromagnetic radiation that still has no mass because they're essentially electrons, and they carry a quantum of energy. And so we can again quantify this. If we want to calculate the energy of a photon using frequency, then we just multiply the given frequency by Planck's constant. And again, we would use the given amount for the frequency for our sig figs. So in this case, if my frequency is 3.55 times 10 to the 17th hertz, then this is 3 sig figs. And I would multiply that by Planck's constant, and I would get 2.35 times 10 to the negative 16 joules. So 1 photon of that frequency would carry that much energy. But keep in mind that since light is continuous, you've got millions and millions of photons all traveling at the same time. And if they're all at this frequency, then they're all carrying this much energy all at the same time. We could also use both of the formulas we've looked at to figure out the energy of a photon that where we're given the wavelength. So let's say I wanted to know how much energy a photon of red light that with a wavelength of 6.47 times 10 to the negative 7 meters is carrying. So we know that energy is Planck's constant times the frequency. And if we rearrange the speed of light formula to solve for frequency, we see that it is the speed of light divided by wavelength. If I substitute this formula in for the frequency here, so what you've learned to do in algebra, then I get that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. And so I would then substitute in my two constants, so Planck's constant and the speed of light constant, and multiply them together. And then I would divide by the given wavelength. And again, the wavelength is what's going to determine our sig figs. So I'd round it off to 3 sig figs. I would get 3.07 times 10 to the negative 19 joules. Now, we've also learned that Niels Bohr was working with these mathematical equations that Planck was coming up with to explain the nature of the atom and this positioning of the electrons within the atom. And remember, he used these theories in order to say that there were specified energy levels for the electrons, that they weren't just wherever in the atom. And so we have these set places where the electrons are normally located, and we call that ground state. So ground state is the lowest energy state of the atom, and that means the electrons are all where they are supposed to be normally. But electrons can also enter an excited state, which means that they have absorbed a certain amount of quanta of energy and have jumped to a higher energy level. So they can make a bunch of these different energy transitions. And they don't like staying in excited state because it makes them unstable. So they're going to give off that energy again in the form of a wavelength of light and jump back down to ground state. And the great thing is that you can take those, you can view these wavelengths of light through a spectroscope. And when you put it through the spectroscope, you won't see a continuous rainbow like it would be if you just put white light through a prism. It would be only certain wavelengths of light, and those are showing the energy transitions that that element is capable of making. We call that an emission spectrum. And that was what Bohr was basing his idea of energy levels off of. So each line of the emission spectrum notes a specific energy level transition that the electrons are making. And so, for example, this would be the emission spectra for Krypton. Now, mind you, not all of the emission spectra is visible. There are some wavelengths that are in the infrared and in the UV ranges, but we can't see them. So we look just at the visible emission spectra when we talk about these. And so we can see that Krypton has We'll do a transition that will produce a band of red light. We'll do a yellow light, green, kind of bluey green, and then several in the purple, almost into ultraviolet range. And so these can be measured using the spectroscope because this little ruler is actually measuring the wavelength of these spectra in nanometers. So this would be like 700 nanometers, and this would be 600 nanometers, and 5 and 4. So this red light is like somewhere around 675 nanometers. And then this yellow one is maybe 580-ish. So, you can make an estimation on what these wavelengths are by looking at the scale. And we're going to look at that in more in depth in our lab.